Hey guys, today we're going to go through chapter 23. This is the start of unit 6. Unit 5 was talking about sample proportions. Unit 6 is talking about sample means. You will notice that there are a lot of similarities. So I'll just kind of be going through those so that you can see how alike they are. So like it says here, we've been working with confidence intervals and hypothesis tests. This is population proportion, things like that. So this time we will be doing it with means instead of proportions. We still have 3 conditions. Notice the third one is different. So it still has to be independent and random. You still need 10 times your sample size. But instead of having 10 successes and 10 failures, this time we want our sample size to be greater than 40. If it is not greater than 40, you're going to need to check your histogram and make sure your histogram is kind of unimodal, and roughly symmetric. So that is the only difference is instead of 10 success and 10 failures, we want a sample size greater than 40. If it's not greater than 40, check the histogram. We were using standard error. There's a formula for proportions. Now that we are using means, you will use that formula down at the bottom. Standard deviation over square root of n. Remember, n is your sample size. So we were doing Z models using Z-score. When you do sample means, we will use the T model, meaning we will use T-score. If you look in the back of your portfolio thing I gave you, you will see a Z-score table and a T-score table. So this is how you could find T-scores. Also, when we were going through all those tests, we were always choosing the Z test, one proportion Z test, things like that. Now we will be picking all T's. So that's where we're going to fill in the rest of those tests. The only difference between the Z model and a T model is a little bit shorter and wider. The reason we do this, William Gossett did it. He made fatter tails for when we have small sample sizes. So this is anytime you just have a few samples, you need more room for error. When doing this, we will be using degrees of freedom, which is coming up. So if you read through this, it says he uses degrees of freedom to determine how fat your tail should be. So the normal model is a specific curve. The T model can fluctuate based on your degrees of freedom. And so it says as the sample size increases, the tails shrink and get closer to the normal model. That just means the larger your sample size, the closer you are to the normal model. That is a good thing. When trying to figure out how many degrees of freedom, we do n-1. So if you want to do these, you can. Basically, it just shows that the larger your sample size gets, the closer you get to the normal model. All right, so we are going to do this example together. It says in 2000, the Bureau of Census reports that the average life expectancy for a person in the U.S. has increased beyond 77 years. Insurance companies track life expectancy information to assist in determining the cost of insurance policies. The insurance company wants to know if their clients have also started living longer. So they randomly select a sample of recently paid policies to see the mean life expectancy of those policyholders has increased. The insurance company will change their premium rates if there is evidence that people who buy their policies are living longer. Does the sample indicate that? So we're going to go through the entire thing. First of all, this is your data, and you're going to want to put it in your calculator. So So I've already put the data in just for saving time on this video. Make sure your data's in. All right, so here's our process. We first have to state our null and alternate. So we have been using P because we've been doing sample proportions. We are now doing sample means. Any guess on what the letter is? M is correct. So our mean is 77-year lifespan. Our alternate, they believe that people are living longer, so it'd be greater than 77. You have to use M. If you accidentally use P on a sample mean problem, they will mark it wrong. All right, we still have the same 3 conditions. Remember, these have to be in context, but because this video has to be short, it only gives me 15 minutes. I'm going to abbreviate. Please do not take the lazy way out, as I am doing solely for this video. Actually write out it in context. But we need it to be random and independent. I need at least, my N was, there were 20 data, so I need at least 200 insurance policies. Now, this one, sample size, that means I have to check my histogram. To make sure it is unimodal and symmetric. In case you have forgotten how to do that, I do want to show you. Remember, go turn your plot on, go to histogram, and zoom 9 will show you. Okay. Now there's a couple of things it wants us to. Oh, it had the conditions right there. Okay. Just a couple of things I'm writing down in case it asks. Our mean of our data. So when I actually run, one variable statistics, I want to write down some of this information. My mean is 78.6. My standard deviation is 4.4. My degrees of freedom, remember this is n minus 1, there were 20, so that's going to make it 19. Standard error is that formula it just gave us. Our formula was standard deviation over square root of n, which when you put that in your calculator, you get 0.984. It's also going to want a t-score and a p-value. Remember, t-score and z-score, same thing. One's on a t-curve, one's on a z-curve. These two we get from the calculator. So we're going to go stat test number 2 this time. Notice we're always going to use t in this unit. Last unit was all z's. This unit's t. So we're doing a t-test. You have two choices up here. You have data and you have stats. It gave us data. So you have to do data. And then you put in your data. My mean for this one was... No, sorry, that's not mean. That's null hypothesis. Null hypothesis is 77. I'm using my list, and I believe that it is greater than. So then it gives you the rest of your information. T was 1.598. My p-value is 0.063. So here's a bunch of information that it may ask you about. Now, what does this mean? So you can say, based on our data, we will retain the null hypothesis because our p-value of 0.063 is greater than 0.05. Therefore, we cannot say that life expectancy has increased. Remember, you still need the same 3 things. You need to say if you're retaining or rejecting. You need to tell why because of your p-value and put it in context. Now, if I was to do a confidence interval, this is stat test. This time we're going to go down to 8, which is a t interval, not z. I'm still using data. It gave me the data this time. It's still an L1, and it wants a 90%, so I need to change that. So my confidence interval, which gives me here, I can write that down, 76.869 to 80.331. So our conclusion here is we are 90% confident that the true mean lifespan is between 76.9 to 80.3 years. Therefore, we retain the null hypothesis because 77 years is, in that interval. All right. Oops. Sorry, guys. Didn't realize it wasn't on the screen. So notice that whether I use confidence interval or p-value, remember, these are just two different ways to get to the exact same answer. So that's how you do those. Now I want to do one more example. This past example used data. This one I want to do it with stats just so you can see how it's going to work. Oops, I'm sorry, guys. All right. So I'm going to let you read this on your own and go ahead and keep going just for time's sake. My null here, you can pause the video and read it, is that my mean is 516, and my alternate is that my mean is greater than 516. So I like to write these down just so I have them. I don't have to flip back and forth. Her mean was 550 with a standard deviation of 36. Again, put your conclusions in context. I'm running out of time on the video, so I'm going to go quick. Actually, they might be listed. There we go. Good. Random and independent. We need the population to be at least 500, and our sample size is over 40, so we don't need to check a histogram. But make sure you write those down. For this one, it wants, so don't forget conditions. My standard error, not standard deviation for this one, is 36 over the square root of 50, which gives me 5.09. My degrees of freedom, there were 50 in the group, so 49. It's still going to want t-score and p-value. These come out of the calculator. So I'm still going to run stat test 2. But this time, it didn't give me data. It gave me stats. It gave me the mean and standard deviation. So I'm going to have to fill that in myself. The mean here is 516. My null. My null is 516. My mean is 550. My standard deviation is 36. I did 50 students, and I think greater than. So it gives me my t-score is 6.678, and my p-value, be careful, p cannot be greater than 1. That's impossible. So if you see a number bigger than 1, there's going to be an e at the end, which means it's actually 0.1, 2, 3, 4, 5, 6, 7, 1. Okay, so how I say that would be, I'm actually just going to read it to you. If you have to play the video back, that would be easier, but I'm running out of time. Based on our data, we will reject the null hypothesis because our p-value of 0, that is basically 0, is less than 0.05. Therefore, we can conclude that her students are performing higher than the national average. Now, so, state conclusion. Just go back and listen to what I said and write it down. What if it wanted the confidence interval? Same thing. I'm going to go stat test, I think it's 8. Still using stats. It does copy your information over, so that's really nice. It wanted a 90%, confidence interval. So my confidence interval is 541.46, 558.54, if you need to see that. All right, and again, I'm just going to read you the conclusion for the same thing. I'm running out of time on the video. So just listen to what I said. If you have to back it up and listen again, that's fine. So my conclusion for the confidence interval, you would say, we are 90% confident that the true mean SAT score for her students is between, oops, I wrote that wrong, 541.41, there we go, 541.46 and 558.54, which is higher than 516. Therefore, we can conclude that her students are performing higher than the national average. So this is sample means, just kind of the introduction. Notice that it is very, very similar to sample proportions with just a few differences. Talk to you guys later.